In this question, we have a power function, y equals x to the power of m, and then we have a differential equation. And if we examine that differential equation carefully, we will notice that the differential equation contains the second derivative as well as the first derivative. So we need to take our power function, y is equal to x to the power of m, and we need to differentiate it 2 times. Of course, we will be applying the power rule to do so. So for example, for y prime, we will multiply m by the coefficient of 1, which gives us a new coefficient of m, and then we subtract 1 from the power to give us x to the power of m minus 1. There is the first derivative. For the second derivative, again, we do the power rule. We will multiply the power of m minus 1 by the present coefficient, which is m. This gives us m multiplied by m minus 1. And then the new power is obtained by subtracting 1 from the old power, so we end up getting m minus 2. So now what we're going to do is take our y prime expression, plug it into the differential equation, as well as our y double prime expression. We'll plug that in as well. So let's go ahead and do that. We've plugged in the expressions for the derivative. We should also notice that the differential equation contains the original y, so we're going to go in there and plug in the original power function. So instead of y, we can substitute in x to the power of m. Now we look to simplify this, and if we look at the first term, we have x to the power of 2 multiplied by x to the power of m minus 2. And recall that when you multiply powers of x, you actually add the powers. So we're going to end up having x to the power of 2 plus m minus 2. But if you look at that carefully, the 2 and the minus 2 would cancel. That would leave us with just x to the power of m. So we have x to the power of m times m minus 1. And then we look to the second term, and we have a similar simplification. We have x to the power of 1 times x to the power of m minus 1. So we would end up with 7x to the 1 plus m minus 1. We're adding the powers again. The 1 and the minus 1 would cancel, and that would also leave us with just x to the power of m. That is still multiplied by m as well, and then we have plus 15x to the m. Now it's interesting because all three terms contain x to the power of m. It's a common factor. We're going to factor it out. So we'll have x to the power of m multiplied. In the first group of terms, we are left with m times m minus 1. In the second group of terms, we have the minus 7 times m. And then in the last term, we have the plus 15. Now we wish to simplify this further. We can take this m and distribute it, giving us m squared minus 1m. And that's going to be further simplifiable because if we look, we've got minus 1m minus 7m. That'll make a minus 8m. Continuing simplifying, we can factor the expression in brackets. Briefly, remember we need two values that add to the middle number and multiply to the last number. And of course, those values will be a minus 5 as well as a minus 3. So we can factor it accordingly. And once we do so, we can now set each of the three terms equal to 0. We do have the product of three terms set to 0. And so we know that we could set each individual term equal to 0. First, we have x to the m is equal to 0. We probably know that there is no power of x that would equal 0. You can sit here and try all day, but no matter what you plug in for m, you won't be able to get an outcome of 0 here. So there's no solution for that first equation. But in the middle, we have m minus 5 equals 0. We add m to both sides, and we get m is equal to 5. And then similarly, in the last term, we end up getting m is equal to 3. So we actually have two answers. Remember that the original power function was simply x to the power of m. And therefore, the two solutions to the given differential equation will be y is equal to x to the power of 5, or y is equal to x to the power of 3. Both of those power functions would satisfy the given differential equation.